Hi everyone, I am Jenny and my topic is the Chinese remainder theorem. The Chinese remainder theorem is an ancient theorem that gives the condition necessary for multiple equations to have a simultaneous integers. The theorem has its origin in the work of the 3rd century AD Chinese mathematician Sanzi, although the complete theorem was first given in 1247 by Qin Zhushao. The Chinese remainder theorem or CRT is used to solve a set of congruent equations with one variable but a different moduli, which are relatively prime, where x is congruent to a sub 1 mod m sub 1 and x is congruent to a sub 2 mod m sub 2, such that x is congruent to a sub k mod m sub k. So let's take a look at this example. The following is an example of a set of equation with different moduli. X is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. The solution to this set of equation is given in the next section. So for the moment, note that the answer to this set of equations is x is equal to 23. These values satisfy all equations. 23 is congruent to 2 mod 3, 23 is congruent to 3 mod 5, and 23 is congruent to mod 7. So here's the solution to Chinese remainder theorem. 1. Find m is equal to m sub 1 times m sub 2 times m sub k. So this is the common modulus. 2. Find m sub 1 is equal to m over m sub 1, m sub 2 is equal to m over m sub 2, m sub k is equal to m over m sub k. 3. Find the multiplicative inverse of m sub 1, m sub 2, and m sub k using the corresponding moduli. Call the inverses of m sub 1 raised to the power of negative 1 and m sub 2 raised to the power of negative 1 and m sub k raised to the power of negative 1. 4. The solution to the simultaneous equation is. So here is the solution to the simultaneous equations. X is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. The answer to the simultaneous equation, you just simply follow the 4 steps. Step 1. Find m is equal to m sub 1 times m sub 2 times m sub 3. The m subs here is indicated mod, which is the m sub 1 is mod 3, the m sub 2 is mod 5, and the m sub 3 is mod 7. Just simply multiply this mod so that you can obtain the answer, which is m is equal to 105. Step 2. Find m sub 1 is equal to m over m sub 1, m sub 2 is equal to m over m sub 2, and m sub 3 is equal to m over m sub 3. Get the answer, just simply substitute the value of m divided by the value of r mod. Step 3. Find the inverse of m sub 1 raised to the power of negative 1, m sub 2 raised to the power of negative 1, and m sub 3 raised to the power of negative 1. So the inverses are m sub 1 raised to the power of negative 1 is equal to 2, m sub 2 raised to the power of negative 1 is equal to 1, and m sub 3 raised to the power of negative 1 is equal to 1. Step 4, which is the last step. So we already have the value of m, which is 105, the value of our m sub 1, which is 35, or the value of our m sub 2, which is 21, and the value of our m sub 3 is 15. And we already have the value of our inverses. The inverse of m sub 1 raised to the power of negative 1 is equal to 2. Our inverses of m sub 2 raised to the power of negative 1 and m sub 3 raised to the power of negative 1, both 1. So let's write the formula. So after writing, just simply substitute all the answer from step 1 to step 3 for this given formula. So after multiplying all the values, the answer or the unique answer must be 23 mod 105. Here is another example for this lesson. Find an integer that has a remainder of 3 when divided by 7 and 13 but is divisible by 12. So, this is a CRT problem. We can form 3 equations and solve them to find the value of x, where x is equal to 3 mod 7, x is equal to 3 mod 13, x is equal to 0 mod 12. If we follow the 4th step, we find x is equal to 276. We can check that 276 is equal to 3 mod 7, 276 is equal to 3 mod 13, and 276 is divisible by 12. So the quotient is 23 and the remainder is 0. Chinese remainder theorem used to speed up modulo computations. If working modulo a product of number, for example, mod or m is equal to m sub 1, m sub 2 to m sub k. Chinese remainder theorem lets us work in each moduli m sub I separately. Since computational cost is proportional to the size, this is faster than working in the full modulus m. Chinese remainder theorem can implement CRT in several ways. To compute a mod m, first compute all a sub 1 is equal to a mod m sub 1 separately. Second, determine constant or the c sub 1 below, where m sub 1 is equal to m over m sub 1. Then combine result to get answer using this formula. Suppose m sub 1 to m sub k are pairwise relatively prime positive integers, and suppose a sub 1 to a sub k are integers, then the system of k congruences x is congruent to a sub I mod m sub I, where 1 is less than or equal to I less than or equal to k, has a unique solution modulo m is equal to m sub 1 times m sub k, which is given by a sub I is equal to m sub I times m sub I raised to the power of negative 1 mod m sub I, and m sub I is equal to m over m sub I for 1 less than or equal I less than or equal k. So, I'll be presenting the proof of Chinese remainder theorem. That's the proof of Chinese remainder theorem. It is important for us to understand and know that proof because it helps us in solving problems with regards to Chinese remainder theorem. Operations performed on the elements of z sub m can be equivalently performed on the corresponding k tuples by performing the operation independently in each coordinate position. Just take a look at this example. CRT or Chinese remainder theorem provides a way to manipulate potential large number mod m in terms of tuples of smaller numbers. Example, let m sub 1 is equal to 37, m sub 2 is equal to 49, m is equal to m sub 1 times m sub 2 is equal to 1813, where our a is equal to 973 and b is 678. Our m sub 1 is equal to 49 and our m sub 2 is equal to 37. By using the extended Euclid's algorithm, m sub 1 raised to the power of negative 1 m mod sub 1 is equal to 34, and m sub 2 raised to the power of negative 1 mod m sub 2 is equal to 4. Taking residues modulo 37 and 49, 973 is equivalent to 11 and 42. The 678 is equivalent to 12 and 41. Next is add the top multiples element-wise. 11 plus 12 mod 37 and 42 plus 41 mod 49 is equal to 23 and 34. To verify, we compute 23 and 34 is equivalent to a sub 1, c sub 1 plus a sub 2 and c sub 2. Mod m is equal to a sub 1, m sub 1, m sub 1 raised to the power of negative 1 plus a sub 2, m sub 2, m sub 2 raised to the power of negative 1. Mod m is equal to quantity of 23, 49, and 34 plus quantity of 34, 37, and 4 mod 1813 is equal to 1651, which is equal to 678 plus 973 mod 1813 is equal to 1651. In conclusion, the famous Chinese remainder theorem managed to raise much interest from the mathematician in antiquity to give commentary in their respective treatises due to the unelaborated explanation given in Sanzi Xuanzing. Muslim mathematician Ibn Tahir should be given credit for cracking the unresolved mystery posed in Sanzi Xuanzing since the 3rd century. Through Muslim mathematicians, the Chinese remainder theorem spread into the works of the European mathematician. Always remember that the Chinese remainder theorem is a theorem which gives a unique solution to simultaneous linear congruences with coprime moduli. Thank you for watching and listening, and I hope I've learned something in this video. Bye!